We touched on vorticity before, and as I have explained before, think of ice skaters who change their rotation speed by stretching out the arms or bringing them together, curling up, and so on. So that's similar idea in terms of stretching the air or water columns and moving off the equator. So you have the planetary vorticity and you have the relative vorticity. We already talked about these before. And potential vorticity is essentially this idea of how vorticity changes based on what configuration the ice skater takes. In the real world, that just means how the fluid depth changes. It's intuitively, you have to imagine that you have, let's say, the thermocline and the upper layer. The upper layer changes its depths based on divergence, convergence, advection, and so on. That would change the vorticity. So we will see that when you take the relative vorticity, planetary vorticity, and divide it by the fluid depth, which is not constant, that is what gives us potential vorticity, which means the vorticity can change depending on how you move, let's say, the center of mass. So here again, the fluid depth is written in terms of the mean depth, the slope that we talked about, which was a function of latitude, because we are only looking at a zonal mean flow sections in most cases, plus the height of the geopotential perturbation and the bottom topography. So here the total relative vorticity is the mean background vorticity. We're talking about basic states. So basic state can have a shear, which is essentially vorticity. You can curl your fingers in the direction of the shear and you get the vorticity direction, right? Plus the perturbation vorticity, which is what the linearization has been all about. Remembering our basic assumptions of this perturbation depth change being much less than the mean depth, and the slope change in the sloping perturbation being much less than the total mean depth as well. We can write 1 over h as 1 over h bar, the mean depth, times 1 minus hs over h bar minus h over h bar. So you look at the figure and make sure you understand how this is done using these scaling arguments. Then you write the vorticity. Basically we have been looking at the flow field induced by the waves. We looked at meridional zonal winds, meridional zonal currents. Now we are going to look at induced vorticity to explain the equatorial trapping. Remembering again, beta is a restoring force. If you go off, you're going to change your vorticity, and there is a pull back by the restoring force. Those are the ideas. So you look at that in terms of the perturbation vorticity, flow field depth, and this function of mean basic state vorticity plus the planetary vorticity. Beta y is essentially the rotational tendency introduced by the fact that Coriolis changes with latitude, and this dependence on the mean depth again. So potential vorticity is going to depend on the depth as well. So we have neglected the second order terms such as zeta h, and qh is conserved quantity in an adiabatic process. This is a derivation that is not so simple, but I will run through it here quickly from the appendix E, because it's not directly relevant, it's moved off, but we will just go through it to make sure. So in that case, dqh dt is 0, so potential vorticity is basically adiabatic heating or cooling can stretch or compress the column, which means potential vorticity is going to change, just like the skater doing this or this, right? That's the simple physical explanation. So looking at our governing equations, which we have looked at already several times, differentiating equation E2 and E1 with respect to x and y, we derive the verticity equation where we have the divergence term here, and this is the divergence of relative verticity and divergence of planetary verticity, and these are the advection of relative and planetary verticities. So if you think of a column, it has verticity. You can either tilt it, you can just move it, you can do all sorts of things. So these terms correspond to those processes in the total verticity balance. So zeta here is of course dv dx minus du dy, the relative perturbation verticity. Then you can write this equation this way, performing the operation of E5 divided by h to get potential verticity minus zeta plus f times E3 divided by h squared. I'm not going to go through these, but you can read up. You get the potential verticity conservation equation which we wrote before. Obviously, you are assuming that there is no heat source which can add or change verticity by the processes we talked about before. So this is the adiabatic case where verticity is conserved here. Potential verticity again is zeta plus f over h, which we can, so in this equation, if we replace zeta plus f over h using our approximations of how h scales with respect to the total depth, we can write the dqh dt equation which we wanted to derive. So for the simple basic states, we have zeta bar is minus du bar dy, the meridional shear we just talked about. That's the basic state verticity or the background verticity. So at any latitude y, for u bar equals constant, du bar dy becomes 0, then the verticity equation simplifies to this form, which is just a function of the perturbation relative verticity dependent on depth and the slope, and the planetary verticity terms that also are affected by the fluid depth. Right? Why am I rushing through it? Not really. I'm just trying to get you to the physics of imagining how the waves and the equatorial trapping of the waves can be explained in terms of vorticity, which means the restoring effect of beta, and how the restoring effect of beta itself is changed by the background state and depth, which is what we had talked about before. So at some latitude y0, this expression is 0. That's our turning latitude, of course. So that equation 648 becomes hq0 is beta y0 times 1 minus hs0 divided by h bar. Consider that is the height of the sloping surface at the equator or at the turning latitude, which we don't want to become negative as we saw before. Consider now what occurs if we move the column at y0 to some latitude. So now we are going to try to move the air column or the water column in the latitudinal direction to squeeze the air column and change the verticity, or expand it and change it. As QH is conserved, as we saw in equation 647, we can write the previous equation with this equation. So 648 and 649. Please flip as you want and listen carefully, because this is very different than when we are writing on the blackboard, right? We have to flip the slides. We get this expression for the latitude y0, which is our turning latitude that we are looking at. So this is the physics of equatorial trapping. Equatorial trapping means the extent to which the waves go off before they become decaying exponential solutions and not waves anymore, and they depend on beta and the equivalent depth of the fluid. Okay, so here the background state is now absorbed into zeta. It is still the vertical shear. So we are explaining now the equatorial trapping process in terms of the vorticity arguments. Vorticity is a very, very critical parameter for both the ocean and the atmosphere, but often we do these things without explicitly talking about vorticity at all. But in this, whenever you do atmospheric physics, it's very hard to get away from vorticity. But ocean, for example, the John Marshall Alan Plum book that I used for my ocean atmosphere dynamics course that's on my channel, they don't talk much about vorticity at all. Whereas if you look at a book like Holton, it's full of vorticity arguments, of course, because Holton is focused only on the atmosphere. Okay.